So another way for us to find volume is using cylindrical shells. And I think, at least those of you that were in my class last year, we talked about this briefly at the very end of the year. But the method is basically taking a section of a curve and taking chunks of it, little tiny chunks of it, and revolving them around whatever axis you are to make little hollow cylinders. So like, toilet paper tubes, basically, that all fit inside of each other to take up all of the space in that solid of revolution. And so effectively what we're going to be doing is we're going to be looking for the lateral surface area of one of these cylinders and then multiplying it by the thickness, and the thickness will be dx or dy. So the formula that we get is 2 pi r times the height, or times the altitude, times the thickness, which is your dx or dy, and then you just use an integral to sum them all together. So let's just take a look at the one that I always start with here. It's sort of got one shell drawn in it, right? So it's just a hollow cylinder. And so we need to find the radius of that cylinder. We need to find the height or the altitude of that cylinder. And we need to determine if that thing's thickness is in terms of y or in terms of x. And then we just do 2 pi rh dy or dx. So anytime you revolve around a horizontal axis, like this one's revolving around the x-axis, the cylindrical shells are drawn with like one of these little rectangles that we put in here in the y direction. So we'll do everything in terms of y. So to think about it like we're taking a very narrow rectangle, pretend that's a rectangle, and revolving it around that axis. So it goes around and you end up with this lovely little cylindrical shell. Everybody good with the concept of what we're doing? Yeah, and then we could draw another one if we wanted to. This one is narrower, right? It's got a smaller radius, but it's got a larger height because it extends further out. And so there's just an infinite number of these little cylinders that sit within each other and take up this entire space. The last one on the right-hand side is just very, very, very short, but has the largest radius, and then the furthest one in has the smallest radius, but the largest height. So this already got everything all labeled out conveniently. Our function was y equals the square root of x. Okay? And so what we did with that was we determined that the height of this thing is whatever this full length of 4 is, minus however far over we go, x. So the height is 4 minus x, and since y is equal to root x, that tells us that x is equal to y squared. So our height is 4 minus y squared. And then our radius, and anytime we're doing these shells, if we're revolving around the x-axis, our radius is just going to be that y value. And if you're revolving around the y-axis, it's just going to be x. Can you guys see what I'm writing now? I don't know. Adrian, you good? Aiden, no, not good. So we've got our radius of y, and we've said anytime we're rolling around the x-axis doing shells, the radius is going to be y. And we've got our height of 4 minus y squared. So all we got to do is figure out the lowest y value, which is 0, and the highest y value, which is 2, and then integrate from 0 to 2. 2 pi times r times h, and then dy. And so what do we get if we integrate that? 2 pi times the integral from from 0 to 2, 4y minus y cubed dy, which gives us what? Integral of 4y ought to be 2y squared minus y to the 4th over 4 from 0 to 2. And the 0 is just going to be 0, so all we really need to worry about is the 2. We got 2 pi times, what does that become? 8 minus 4. So 8 pi units cubed. And obviously this one could have been done even actually easier using the disk method, right? If we're doing the disk method, we'd be slicing it vertically, so it'd all be in terms of x, and we do pi times the radius, which the radius would be root x squared dx from 0 to 4. And we should see then that this is pi times root x squared is x, and so that becomes x squared over 2 from 0 to 4, which also comes out to be 8 pi. So we can do it either way. In this case, the shell method was a lot more complicated, but for many problems, it'll be a lot easier. And for some problems, not on the AP test, but for some problems, it's the only method you'll be able to use. So let's see if we can do this one. Everybody good so far? All right, so we've got the region in the first quadrant that's bounded by 4 minus x squared. So I've just drawn the first quadrant part of that. And y equals 3x. And x equals 0. So we're talking this section right here. It's bounded by those 3 lines. We're going to revolve that around the x-axis to form a solid. So if we're going to revolve this around the x-axis, we should draw in a rectangle and make the little cylinder here. And so this is what all of our cylinders look like. And they should have a radius that's just going over from the y-axis to some value x over here. So your radius, like I said before, if you're just going around the y-axis, is just x. And then it should have a height that is the upper function. And our upper function is the parabolic function, 4 minus x squared, minus the lower function, which is 3x. Everybody good with that? Okay. And then lastly, we need to figure out the furthest left x value. Well, the furthest left x value is 0, but we need to figure out where they intersect. So we got to find the furthest right x value, which will be 4 minus x squared equals 3x to see when they intersect. So we got x squared plus 3x minus 4 equals 0. Or what does that come out to be? X minus 1 and x plus 4. So they intersect at x equals 1 and x equals negative 4. Clearly, we don't care about negative 4 because that's not in the first quadrant. The x equals 1 value will be. So we're going to integrate 2 pi from 0 to 1 of our radius times our height. And dx. We know it's dx because the thickness of this is going in the x direction. Good or no? Y'all are all right with that? All right, let's real quickly evaluate. So we got 2 pi times, let's see, that's the integral of 4x. Integral of 4x ought to be 2x squared. Then we got minus an x cubed, so that'll be minus x to the 4th over 4. And then we got a minus 3x squared, which ought to be minus x cubed. And we're going to go from 0 to 1. The 0 will make those all 0. So we've just got 2 pi times, let's see, 2 minus a 4th minus 1 minus 0. And what does that give us? That's 3/4 times 2 pi. So that ought to be 3 pi over 2. Good or no? Yes, Molly, if you want to use this method on the AP test, you are more than welcome to. It's just none of the problems will require you to. So yeah, you can use it, and sometimes it makes the problems a lot easier, but every problem can be completed using a disc or a washer or the cross-section method that we talked about yesterday. All right, I think we'll just set these ones up and not actually evaluate these ones out. If we want to use shells to find the volume of the solid that's generated by revolving 2x minus 1, x equals 0, and root x around x equals -2. So first we'll sketch what this looks like. So here is root x. 2x minus 1 is below that, and we're also bounded by, what are we bounded by? X equals 0. So we're looking at this region right here. And we're going to revolve around the line x equals -2. So if we were to revolve around that line, that means that the rectangle should be parallel to that line. So there's my little rectangle that I'm revolving around here. And that tells me that the thickness of it ought to be dx. And our height ought to be the upper function, which is root x, minus our lower function, which is 2x minus 1. And then our radius is the distance from here to our typical rectangle. Our radius is 2 full units, right, to go from -2 to the y-axis, plus x more over, so 2 plus x as our radius. And so this integral should become the integral, or 2 pi times the integral from 0 to wherever these intersect, so we gotta figure that out. When does 2x minus 1 equal root x? That's probably pretty easy to see. If you want, you can square both sides and solve it. But probably note that that's it, x equals 1. Just by a visual inspection of that equation. So we have 2 pi times our radius times our height dx. And we'll call that good enough for now. No reason for us specifically to go through and evaluate that. Okay. I'm waiting, Nick. Is there a reason I'm waiting, Nick, or no? The area left of the y-axis? What area left of the y-axis? We're bounded by x equals 0.
Well, okay, like, you know how like in washers we would like take the area of like the area that's like we're looking for minus like, you know, like the area of the upper function minus the area of the lower function.
Yeah, we did that. That's our height.
So like we're only looking for like this one, we're only looking for like there's a part in the middle of like that cylinder that's empty, right?
Correct.
So do we not need to like subtract that?
Yeah, that stuff's not included because we're only starting at 0 and going to 1. So if we were starting at -2 for our integral going to 1, then we'd have to subtract off the part from -2 to 0. But
okay.
Yeah, that makes sense.
Yeah, that does.
Cool. All right. So what if we were to revolve this around the line x equals 5? So I'm going to redraw our picture here real quick. It's going to look just as atrocious as it did the first time. Is our height of our rectangle going to change? Or our thickness? It's still going to be dx, right? Didn't do that very well. Our height's still going to be the same, right? And our dx is still going to be the same, but what's going to change is our radius. And our radius is this section, which this is 5 full units, and this little piece here is x. So our radius changes to 5 minus x, but everything else ought to stay the same. So we ought to get 2 pi times the integral from 0 to 1 of 5 minus x times root x minus 2x plus 1 dx. Everybody okay with that or no? That's the basic idea behind shells. That's all we're going to do with that. Since it's not on the AP test, I just want to at least mention it. Make sure we know it exists. So, any questions, any issues there? All right. We're going to move on with arc length here in just a second. All right, we're going to develop a formula for how to find the length of any arc, or basically how to find the length of any curve in the XY plane. We're also going to apply this in polar curves and vector functions and parametric functions and all of that. So we'll see how much of this we can get through today. We may have to touch on it a little bit tomorrow. Any thoughts about how we might find the actual length from A to B? Not the distance, right? Not the distance between them, but the actual length of it. Molly, did I not post these in advance? No, oops, sorry. Is it helpful to you guys if I do that right now? I can do it right. I mean, it'll take me like 2 seconds if I do it right now. All right, give me 1 second. All right, so normally, if we're trying to find distances in the XY plane, what do we use? Yeah, normally we use the distance formula, right? And what is the distance formula? Just remind me, what's that distance formula? It should be the square root of the change in x, right? x2 minus x1. We're just going to write it as delta x squared plus the change in y squared, right? Delta x squared plus delta y squared, square root. That's the distance in the plane. Everyone would agree with that? I hope you made it this far into second calculus class, so I assume you're good with that. That, if I were to use that distance here as an approximation for the actual length of the curve, I'd be way off. Would you agree? Hopefully you would agree that that would be horrible. That would be just atrociously off. Well, what if I did this? What if I split it up and did this distance plus this distance? Do you think that would be better? Probably be better. Still wouldn't be very good though, would it? What if I broke it up into all of these pieces. Maybe better? Getting closer to the right value? Do you guys agree with that? Okay. Well, one would probably imagine that the more pieces I broke that up into, the more accurate of a representation of the actual length I would have. And if I were somehow able to break that up into an infinite number of little pieces of straight lines there, an infinite number of those and their lengths summed together should be probably an exact value for the length of that curve, right? That's kind of what we did with the areas of the rectangles. We said, let's make these rectangles as thin as possible and sum them all together. Let's make them effectively 0 and sum them all together. Well, if we were to effectively make the distances from one point to the next 0 and then sum together all of those distances, we should end up getting the exact length of the curve. And if we have a curve that we know the equation of, what is the best approximation for how much that function's y value changes on a little given interval? How do we approximate a change in y on a very small interval? Think back to when we did differentials. We just use a tangent line, right? We use a derivative to do that. And so the derivative tells us how much y changes given a small change in x. So we should be able to say this is the same as delta x squared plus the derivative, giving us the slope of the tangent line, right? Times however much x changes. The change in y ought to be in a straight line, f prime times the change in x, right? The slope of the tangent line at any given point times the amount x changes. Would you all agree with that? I hope. Yes, no, maybe. Nobody's responding anymore. All right. At least Aiden understands, and maybe Adrian. You have a problem with that, Adrian, or no? And if we're using okay, so no, Nick, it's not the change in y times the change in x. It's the slope of the tangent line at whatever point we're at times the change in x. Because we're using these tiny little linear pieces to approximate the amount that the function itself changes. And so the change in the x is just the change in the x, and the change in the y using a tangent line is just whatever the slope is times however far over I go in x, right? I mean, your f prime, right, is just your delta y over delta x. And if I multiply that by delta x, that ought to give me delta y, right? And so that's effectively what we've done here. We've said f prime is a change in y over a change in x. It's a slope. And so we're multiplying it by the delta x to just turn it back into a delta y. Does that help everybody that maybe was a little confused? Yeah, okay, cool. So now we would hopefully note that both of these have a delta x in them, in fact, a delta x squared in them. So I could factor out that delta x squared. And we'd have 1 plus f prime of x squared. And the delta x squared inside the square root could come out as a delta x. And what is the delta x when we're talking on very, very small scales? That change in x, we refer to that as a dx. And so we end up, I'm going to write this here as 1 plus f prime of x squared times delta x. But when we sum together all of these little pieces, we refer to this delta x as the dx, and this becomes an integral from a to b of the square root of 1 plus f prime of x squared dx. And so directly from that distance formula, we are able to write a formula that represents the length of any curve in the xy plane. Does everybody see that? How that's formed? Yeah, I'm waiting. As requested. Do you have a question, Molly, or are you just writing things down? Oh, oops, sorry. Yeah, I got my parenthesis in the wrong spot there. Oh, I'm going to erase the whole thing. All right. Actually, that wasn't the problem. This will fix the problem. There we go. That's what that should have looked like. Sorry, I don't know why that squared would have continued on to the 1. It shouldn't have. I just wrote my parentheses bad. Better now, Molly? Okay. Everybody feel okay about that formula? That's a formula you're going to need to know and have memorized for the AP test. Cool. So let's see if we can do this. Let's find the length of the arc of y squared equals x cubed from the point 1, 1 to the point 4, 8. And so if we were to square root this, we end up with y equals x to the 3/2. And the upper portion of this just looks like that. So we got a point at 1, 1, and we got a point at 4, 8. And so we want to know how much actual length is there of that arc. So first off, we're going to say that y is x to the 3/2, and that our formula ought to be an integral from 1 to 4, so from our x value to our other x value, of the square root of 1 plus the derivative of this. So what's the derivative of this? What's y prime? It ought to be 3/2 x to the 1/2, or 3 root x over 2. And if I were to square that, that's what's got to go in here. What's y prime squared? That ought to be 9x over 4. Everybody good with that? And how would we solve this integral? Yep, should be a u sub. What's the u sub that we'll use for it? U equals, should be everything inside that square root. So 1 plus 9/4 x. So du will be 9/4 dx. So we'll put in 4/9 outside, and we'll put a 9/4 right there. And we should be able to rewrite this as 4/9 of the integral of root u du, and 1, if we plug 1 into our u value here, what do we end up with? Should end up with 13/4. And if we plug in, what is that? Plug in a 4, we should end up with 10. Everybody good with that? So we got 4/9, and then root u becomes 2/3 u to the 3/2. And the numbers on here become a little bit unpleasant, 13/4 to 10. And what does that come out to be? Approximately. Just give me an approximation for that. It's probably easier if you just approximate it from the original integral, but it's good to know how to do it. Make sure we're not forgetting our basic integrals. So what's the integral from 1 to 4 of root 1 plus 9x over 4? Anybody? Okay. Anybody else agree? 3.393? I hope that's right. Anyone else? Did you do it wrong, Darius? Yeah, I got 7.634. I just typed it into Desmos, and that's what I got. So. At least I've already got a nice box for my answer there. All right. I mean, there's no variable other than units, and we won't. I mean, you don't need to write units next to it. If I said that something was model, if the length of a garden hose, or if the garden hose was laying out at whatever, some equation, and it was some number of feet, then put feet, but otherwise, you don't need to write units to attach to that. All right, so we should see that this is not too bad. Let's set up an integral to find the length of y equals 1 plus 6x to the 3/2 from 0 to 1. So what do we get? First off, it should be an integral from 0 to 1, right? And it ought to be a square root of 1 plus, and it ought to be the derivative of this. So what's y prime? Y prime ought to be 9x to the 1/2, or 9 root x. And if we square that, it ought to just be 81x dx. And that ought to give us the entire length of that function from x equals 0 to x equals 1. And what do you get if you do that? We'll just approximate these. Most of these don't come out to be real nice answers. Some of them will, but most of them do not. this in right. Somebody let me know if this is what you got. 6.103. Perfect. Good. All right. Let's figure this one out. Let's do this one all the way out by hand and not approximate it. So we're going to find the length of y equals the natural log of secant of x from x equals 0 to x equals pi over 4. So in order to do this, first thing we're going to need to know is what y prime is. So what's y prime going to be? It's the derivative of natural log of secant, which ought to be 1 over secant. Sorry about that. My kid was asking me where his kazoo is, so I'm about to have a headache. 1 over secant times the derivative of secant, so times secant x tangent x. And obviously we can cancel out the secant x's to make that just tangent x, and so y prime squared ought to just be tangent squared x. Everybody good there? So our integral ought to be the integral from 0 to pi over 4 of the square root of 1 plus tangent squared x dx. And how are we going to simplify that down? 1 plus tangent squared ought to be equal to secant squared, right? And the square root of secant squared ought to just be secant. So this now just becomes an integral from 0 to pi over 4 of secant x dx, which we know is natural log absolute value secant x plus tangent x, because you did a good job memorizing all of your integrals. And we'll just do that from 0 to pi over 4. And what should that give us? Natural log absolute value of the secant of pi over 4. What's the secant of pi over 4? That ought to be something that you all unmute yourself and shout out the answer immediately to, or type it immediately in the chat because you know all the unit circle values. Oh, good. Root 2, thank you, Nick. And then the tangent of pi over 4 ought to be 1. And then we'll get minus the natural log of the absolute value of the secant of 0. What's the secant of 0? That ought to be 1, right? Plus the tangent of 0, which is 0. And this is just a natural log of 1, which is 0. So we end up with the natural log, and we don't need the absolute value anymore because obviously that thing is positive. Good or no? Cool. Let's do another one. Then we're going to talk about some caveats to this, some issues that we might have. So we're going to find the length of the parabola y squared equals x, where x equals y squared from 0, 0 to 1, 1. And so if we want to do this in terms of y, we can. So we can, instead of doing this as y equals the square root of x and doing that from 0, 0 to 1, 1, and finding the derivative of root x, which isn't that hard, we can also do it in terms of y. And so then instead of finding dy dx, we'll just find the derivative of x with respect to y. We'll find dx dy. And what should that be? What's the derivative of the function x with respect to y? Yes, it's 2y. And so that squared ought to be there's no dy, Nick and Darius. There's no dy attached to it, right? It's dx dy is just 2y. It's just like taking dy dx if y was equal to x squared, dy dx is 2x. So we're just doing it as if our function was the function x equals something in terms of y. And so we can integrate this from the y value of 0 to the y value of 1. Just specifying the y values that we're using because we're doing this in terms of y. Root 1 plus 4y squared dy. Everybody good with that? How would we solve that integral? Besides just using your calculator. If we wanted to go through, we could do a trig substitution, right? We could do a tangent substitution. But we can just approximate it. I don't mind just doing that for now. What does that come out to be? Hopefully I typed that in right. 1.479. Y'all agree with that? Yeah. All right. So one thing that we want to note is that if the derivative of our function is undefined somewhere on the interval we're looking for, so if there's a corner or cusp or a vertical tangent line, we got to find a way to deal with it. So one way to deal with it is to split it up into multiple different pieces. But another way to deal with it is by doing what we just did with this last one, which is rewriting the function in terms of the other variable. So here we have y equals x to the 1/3, and with any luck, you should know what y equals x to the 1/3 looks like, right? There's y equals x to the 1/3 with a vertical tangent line at x equals 0. And so the vertical tangent line at x equals 0 causes a little bit of a problem, right? That's a place where our derivative is undefined. And so what we need to do is we can convert this into the function x equals y cubed and do it all in terms of y. Because if we do it all in terms of y, we're thinking about this as if it's been flipped and that's a horizontal tangent line rather than a vertical tangent line if we do it with the x and y variables flipped around. Does that make sense to everybody? So we're going to find dx dy again as 3y squared, and squaring that is 9y to the 4th. And so we're going to just integrate from the y value of -2 to the y value of 2 of the square root of 1 plus 9y to the 4th dy. Good or no? You guys agree with 17.261? Cool. All right, let's do another one here. What's wrong with this one? Yeah, the absolute value is causing what to happen at x equals 0. It's giving us a corner, right, at x equals 0. So what does this function look like if x is less than 0? If x is less than 0, we've got x squared. And when x is negative, when you take the absolute value of it, you take the opposite, right? So that would become a plus 4x minus an x, or x squared plus 3x. Everybody agree with that? And when x is greater than 0, you take the absolute value of it, the sign stays the same. So this is x squared minus 4x minus x, or x squared minus 5x. And so we can take this one and just split it up into two different pieces. We'll go from -4 to 0 of the square root of 1 plus, and then what do we end up with here? The derivative of that's 2x plus 3. So 2x plus 3 squared dx, and then we'll add to that an integral from 0 to 4 of the square root of 1 plus 2x minus 5 squared dx. Everybody good with that? All right. And we can just approximate those if we want to. But how would we go about doing those? Those would be trig substitutions, right? We'd like 2x plus 3 equal tangent theta for the one on the left, right, if we wanted to. And for the one on the right, we'd want 2x minus 5 equal tangent theta. And we could do some substitutions with the dx and all that. And, yeah, it'd be a little bit of a pain because we'd end up with some secant cubes in there. But that's the basic process of it. And what does that come out to be approximately if we do the whole thing in our calculators there? $19.556. Yeah, sounds good to me. All right, the next thing, let's see, today's Thursday, right? I don't think we're gonna have time to get through the parametric stuff today. Yeah. I think we'll stop there.